The second submodule deals with determining protein structures. The main methods we'll be looking at are SAD, or single wavelength anomalous diffraction methods, and molecular replacement. They both have their advantages and disadvantages, but they're widely used to generate a lot of structures, and over time they've gotten to the point where they're pretty easy to use as long as you have good data. So there's a little bit of theory in here about what diffraction data actually are, and some things to look for. Whenever you look at a protein crystallography paper, there'll always be in there somewhere some kind of description of X-ray data collection and refinement statistics. And they probably don't mean much to most people because you don't know how to interpret them, but maybe by looking through this a little bit to help understand better why we care about them. Of course, some of the obvious things are things like resolution. So the higher the resolution or the smaller that number, the easier it will be to resolve the positions of atoms within the structure. So the lower the resolution, the better. Once you get down to very low resolution, the data sets can be large, and sometimes just processing the data can be challenging. But for the most part, resolution between 1.5 and 2.5, if you can get within that range, that's pretty great. Better is always, of course, going to be clearer, and as the resolution drops to around 3 angstroms, 3.5, sometimes it can be hard to interpret certain things. Some residues start to blend together, like a valine and a threonine residue are going to look very similar, and cysteine and serine are going to look similar. So some of the residues that are not necessarily isosteric, but kind of the same size, would be hard to interpret. But as long as you know what the sequence is, you should be able to fill in the correct residue. But it does make things a little bit more difficult to work with, especially in regions where maybe the electron density from the maps that we generate with this method is not very good. But something else like redundancy or completeness or RSIM with that. So I get into these values, but essentially something like RSIM is a measure of the quality of the data. And the lower that number, the better. It gives you an idea of what to expect with the maps. Now, of course, the most important thing is, what do the maps look like? Are they interpretable? Are you able to use them to build your structure? That is important. But from a numerical, statistical basis, this is something that is often the first thing that I'll look at when I look at the quality of data to determine that. So there's some discussion in here about it. As far as solving structures using SAD or MAD phasing, we'll be focusing on SAD phasing. Using Phoenix for this is relatively straightforward. There's a series of programs that we use. One is called AutoSolve, which uses program solve and resolve. Mentioned this in the introductory video that we used in the past to solve structures. It works very well. And the nice thing about this is that once you get into that application, it's a matter of adding your data. You will need to add a few more pieces of information, like what is the anomalous scatterer, which when dealing with SAD phasing is often selenium. So selenium is a heavy metal or heavy atom anyway that's put into these proteins often through a method. Growing protein with a selenomethionine derivatized protein. We use selenomethionine oxytrophic organisms to do it, and for example, E. coli. So they're grown in minimal media where the methionine has been replaced with selenomethionine, and they'll grow selenomethionine derivatized protein. So that's nice because that means everywhere there's a methionine, there's a selenium atom, and every protein usually has several. So several anomalous scatterers will make for a really nice anomalous pattern, and it makes solving the structure pretty easy. And one other major convenience about selenium is it has an X-ray absorption edge around 1 angstrom, which is around the wavelength where we normally collect that data anyway. So it's a pretty convenient way of doing that. Now, some proteins cannot be expressed that way. If you're getting them from protein expressed from human tissue or another animal, we're not able to do that. So you have to find other methods. But there are. One method that's handy is using the anomalous scattering signal that comes from sulfur. Sulfur scatters at a much longer wavelength, but it has been shown to be useful as well. The technique would essentially be the same. It's just the signal's not as strong. But sulfur phasing is also a great technique to use if you have very high quality data. Absolutely can be used to solve structure. So I go through, there's some screenshots of the different methods and how to go through with the example that we specifically have, and then a picture of a program called COOP that has the protein structure that was built through AutoSolve and then some electron density. And electron density looks pretty okay. It's not great because at this point there hasn't been a large level of model building and refinement, which will improve maps on further iterations of it. But you can see, for example, this tyrosine residue looks pretty good. There's some electron density missing on this proline residue, but you can clearly tell that it's there, and the oxygen atoms that are part of the peptide bonds are positioned correctly. So, and if they aren't, you can go into COOT and use it to change those things, which discuss in the third submodule. When dealing with molecular replacement, this is becoming far and away the most common technique for solving structures because there's so many known structures of proteins already. All that molecular replacement requires is a protein structure that we believe to be similar to the structure we're trying to solve. And because there's only probably so many ways proteins can fold, we're getting to the point where a lot of the protein folding space has been discovered. In the event that you don't have a protein that you think is structurally similar that has a known structure, we now can use AlphaFold to put one out. You can always try that. If it doesn't work, then it's back to the drawing board. But AlphaFold has been used to fold, it can be used to fold basically anything. So this is a very handy procedure that's pretty fast and relatively easy to use. Basically, you take your protein sequence, go through and find a comparator by doing a blast search, by looking specifically for proteins with known structures in the protein database. And from there, you just choose one of the structures that comes up. Usually just pick the one that has the highest sequence similarity. And from there, download the PDB file and use it as the search model to try to find the structure of your protein. So the idea behind this is that in order to get electron density map, you have to solve the phase problem. The phase problem is solved by taking phases from a known structure and using them on your data. And if they look similar, then it should work out. In the case of the anomalous diffraction methods, you're getting phases from the anomalous scattering. But in this example, you're getting phases from a known structure. And so it does run into the problem of what we call model bias. So if your proteins are similar, but there's some large difference between one structure and the next, it will be a challenge to try to get around that to make sure that your structure looks like yours and not like the one you compared it to. But normally through successive iterations of model building and refinement that can be dealt with. So molecular replacement is used to get a structure. And of course, we also have this here. Now the search model, of course, is going to be what is put in there. So the residues have to be changed to the correct one. But over time, with again, successive iterations of model building and refinement, fix that. So it goes through some strategies on how to find good molecular replacement candidates. And the submodule also describes how to use anomalous methods that can be used to solve structures in the event you don't have a comparison. Sometimes may have a molecular replacement model that works, but having anomalous scattering data is beneficial because there is a model bias with that. You're looking at data directly. You're collecting data directly from your structure instead of from using another known structure to compare. But at the end of the day, you work with what's best, and a combination of two techniques can be useful at times where a molecular replacement model is not readily available.